In the previous video, we explored the most basic optimization algorithm for AI models, gradient descent. In this video, we'll take a closer look at other optimization algorithms, including SGD, momentum, RMSprop, and atom. The gradient descent algorithm is one of the most widely used optimization methods when building AI models. In the learning process of AI models, it's important to reach the global minimum rather than getting stuck in a local minimum. However, depending on the initial conditions, the function may end up at a local minimum instead of the global one. This limitation becomes especially prominent in nonlinear functions. To overcome this, various optimization algorithms have been developed and are used today. In AI model training, based on the amount of data used per iteration, we can categorize the process into three types: batch, mini-batch, and stochastic gradient descent. The batch algorithm refers to using the entire dataset for training and then updating the model all at once, which is generally what we mean when we talk about the gradient descent algorithm. The mini-batch algorithm, on the other hand, divides the dataset into smaller groups, or mini-batches, and updates the model after training on each mini-batch. Lastly, the stochastic algorithm updates the model after training on a single data point. To explain using the diagram below, in the batch algorithm, the entire dataset is used for training in one go, so there's one round of training. In mini-batch, since the data is divided into 3 mini-batches, training is conducted on each batch, resulting in a total of 3 rounds of training. Meanwhile, in the stochastic algorithm, training happens after each data sample is used. So with 9 data points, there are 9 rounds of training. Now, let's take a look at the characteristics of the batch, mini-batch, and stochastic gradient descent algorithms. The batch algorithm computes using the entire dataset and makes an optimal update once per iteration. Since it uses all the data, this process can be time-consuming, especially with large datasets. The mini-batch algorithm splits the dataset into smaller batches and calculates gradients for each one. This method balances the efficiency of stochastic gradient descent with the stability of batch gradient descent. Stochastic gradient descent, on the other hand, randomly selects a single data point for each update. This causes the gradient to fluctuate frequently, making the optimization process less stable, but it allows for faster updates and lower memory usage. Let's further compare the characteristics of batch, mini-batch, and stochastic gradient descent. When we look at how the cost function decreases during model training, the batch algorithm uses all the data, so it reflects the average trend. As a result, the cost function decreases smoothly with minimal fluctuation. In the mini-batch algorithm, since each mini-batch contains only a portion of the entire dataset, the gradient varies slightly between batches. This causes the cost function to decrease with some moderate fluctuations. With the stochastic algorithm, each data point provides different information, resulting in significant variability. As a result, the cost function decreases with much larger fluctuations. While it updates quickly, it can lead to more instability in the optimization process. Now let's explore another AI optimization algorithm, the momentum optimization algorithm. Momentum refers to the concept of acceleration and inertia. It determines the direction and size of the current update by considering the direction of the previous update. This adds the idea of inertia to the gradient update, making the path smoother and more efficient. Similar to how a ball rolls down a slope in a bowl, gaining speed as it goes, Momentum reduces the zigzag movements often seen in stochastic gradient descent, leading to faster convergence. Next, let's take a look at the RMSprop algorithm. RMSprop is an adaptive learning rate algorithm that adjusts the learning speed based on the magnitude of the gradient. When the gradient is large, it reduces the learning rate to avoid overshooting the optimal point. On the other hand, when the gradient is small, it speeds up the learning rate to reach the optimal point more quickly. You can imagine it like a ball rolling down a slope. It moves slowly on steep slopes and faster on gentle slopes. Lastly, let's discuss the atom optimization algorithm. The atom algorithm leverages the inertia effect from the momentum algorithm to achieve faster convergence, meaning it uses previous gradient information to make the gradient updates quicker and more efficient. It also incorporates the learning rate control feature from RMSprop, adjusting the learning speed based on the gradient size to enhance stability during training. Because of this combination, Atom shows fast convergence and good generalization, making it the default optimization algorithm in most deep learning models. In general, the Atom optimizer tends to offer the fastest and most stable convergence in most cases. However, depending on the problem, other optimization algorithms may be more effective. Therefore, it is recommended to experiment with different optimizers and select the one that works best for your specific application.